days I work for the Deutsche Börse, and I've been dealing with some of the RDMA issues at the Deutsche Börse. And I've been talking about this last year, about the various issues that we had to face to stabilize the platform. And so this year we considered upgrading the platform, modernizing the platform, and found a technology direction for the future. And this is about a component that we are trying to develop, what we have developed, and that we're trying to contribute to the open source community that will enable us to migrate easier from our old platform to a new platform. And that may also be useful for other purposes in the RDMA community. So we basically decided to migrate away from InfiniBand and to use Ethernet with ROCE, the RDMA extensions, because it's easier for us to handle. And we have a large base of technologists who are experienced with Ethernet, and we can leverage our community Ethernet experiences over the last 10 or 20 years. And so we hope that this will be easier to manage for us. InfiniBand has been kind of a niche technology and was only used for the core of the platform, and our network department didn't want to deal with it. So now if it's Ethernet, they probably can handle all of that. So this is the basic design of the platform. Basically, this is a setting in 2 different rooms, and those are separated by a very strong firewall. So if the bomb explodes in one room, the other room can take over and threading can continue. And so there are physical redundancies as well as other redundancies. We have 2 fabrics. Every host is connected to both fabrics that can usually operate in different modes. One of them is production data, where the really critical data is being communicated. And the other one is administrative data, where there is diagnostics and stuff like that. So usually the intent here is to minimize the overhead of the production data and ensure that the lines are always free for the important data and keep the administrative data in a separate fabric. In a failover case, any server can choose to elect the other fabric as a backup. So then the performance of the overall system will degrade, but the system will continue. Each individual service, each server or each service on each server can fail at any moment, and there is a backup system that will take over and continue processing the data, and the disruption to the end user is minimal. So we have about 300 to 400 servers right now, and with these redundant links in operation. And this has to be working basically day in, day out with only minimal downtimes in order to enable global trading and then kind of keep the world economy moving, because this is a significant part of the world economy that goes through this system. There are other systems that push data to the system, but this is the core of the system, and it's based thoroughly on RDMA technology. And it's based on multicast that we are doing via the Confinity LLM middleware. So we don't do unicast communication, but we use RDMA communication channels. That allows us one-to-end communication in a scalable way and in a very low latency way that is essential for financial applications. So the multicast data is 99% of the data. Unicast is only be used in case something goes wrong. If a server does not get data from a multicast channel and has to ask, oh, I didn't hear you correctly, resend the data, then the unicast channels will come into operation to backfill the stuff that wasn't received. So in a failure scenario, or when things go wrong, the percentage of unicast may grow. If the system is healthy, then almost all traffic will be multicast. And so what we think about doing is a gradual migration away from InfiniBand by putting in gateways and then moving into Ethernet with ROCE. So we're having the same API to the middleware, and the middleware works in the same way with the RDMA interface, but the underlying platform changes. So we want to be able to migrate single hosts and multiple hosts to the new technology, and gradually do that gradually until the migration is complete, until we can take out all the old InfiniBand switches and just operate on Ethernet switches. So a typical single server has 2 RDMA links, one for the production data, one for the administrative data. These can back up each other if necessary. If one fails, stuff can go through the other. What we have there right now is QDR InfiniBand, and this is pretty old. I think it was 10 years old. 10 years ago or so, this was deployed. And we would like to move that from QDR InfiniBand to 25 gig ROCE. 25 gig ROCE is very simple to handle. It's just the regular strands of fibers that we also have with 10 gig technology, and we can use SFPs, which reduces the complexity and makes it very easy to handle. The data rate is comparable because InfiniBand is calculated in the bits that go over the wire, whereas Ethernet capacities are calculated by the payload that we get through the wire. And so we have actually a rough speed equivalent there. In addition, then these servers also have other links like the access LAN, where other people can access the stuff for diagnostics or modification administration. And then there's a network that allows access to the sending of market data. This means event happened in the market, and we are spreading those new price informations. And then the order data, where customers send in their desire to purchase a certain item at a certain price, and then the systems will process the order, and then if it matches, then they will create market data. So the main issue of the migration is because of the age of the QDR fabric, and the problem is there that we are aging in such a way that the vendor no longer supports our hardware. These are old QDR and FDR switches, as well as cables that are gradually going out of support. The fabric speed itself has always been seen to be sufficient, and we really don't need to do much about that. We seem to have a lot of headway there. The main issue where we are using the RDMA fabric is for speed and effectiveness of basically remote process communication between the nodes in the fabric. So what we've seen also with QSFP is the ease of handling. QSFP has thick cables and it's more specialized, and often this is not something that the Ethernet specialists that we have are used to. SFP is something that's widely used everywhere in the financial industry. 10 gig is basically the standard for how everybody connects to the stock exchanges these days. And so using SFP technology there will generalize the technology even for the fabric and allows us to move off a relatively esoteric QSFP connection. So if we have volume issues, we can actually aggregate the links. And so the switches allow us to actually have single links that can be 50 gig or 100 gig in case one of these servers needs more capacity. So we think this is going to be a good future configuration for our fabric, and this is how we want to migrate. So this is now an example how we can migrate one system here. We build bridges on both of the administrative network as well as the production network that convert the traffic from InfiniBand RDMA to ROCE RDMA. And so these bridges basically have two interfaces, a 100 gig Ethernet interface and an EDR interface. And they connect on one side to a 100 gig Ethernet switch for the ROCE side. And on the Ethernet side, we have an EDR switch that then connects via FDR to the nodes. Initially, we can start like depicted here with two different gateways that just convert these things for one host. And then we can gradually move servers over to the new fabric and enlarge that and gradually grow that until we can convert the whole thing and get rid of the other things. This is also only shown with two bridges. This is basically the first situation there where we convert one host on one side. We ultimately will have two bridges on each side, so that also the bridges are redundant, and if one fails, the other one can be used as a backup. And also that the fabrics and all of that stuff is harmonious in the way it was designed to have redundancy everywhere. So once we are finished with the migration, we think we will decommission the switches as well as the InfiniBand switches as well as the bridges finally. And the system will be entirely consisting of InfiniBand switches, of Ethernet switches that will do 25 gig and 100 gig and 50 gig connections. That brings us to the bridge. So there is a difference between Ethernet, ROCE, and InfiniBand. So we need to be able to convert the traffic between those two technologies. And this is how we do this. So this is the hardware that we're using. The bridge is just a regular one-use server, and it basically has a ConnectX 6 in there, a dual NIC. And you can configure this system to have one link on Ethernet and one link on InfiniBand. And so the bridge has a connection that's higher volume than the nodes to the switches on either side. So there's a 100 gig switch, for example, for Ethernet. And then we have a couple of nodes connected to that network via the 25 gig links. The same thing is going on the other side. We have an EDR connection to an EDR switch, which is a 100 gig InfiniBand basically. And then we go via the legacy links and the legacy InfiniBand system to the various end nodes via the QDR links that are in existence and have been there for a long time. Then we needed some bridge software, and there was nothing there. So what we did is we just took an unmodified Red Hat Enterprise Linux, and we wrote this IB to ROCE bridging software. That is an open source project that we developed on GitHub, and that we want to contribute as part of the RDMA core subsystem or something or somewhere else. So what this IB to ROCE what code does, it supports basically RDMACM based bridging. RDMACM is a certain layer within the InfiniBand stack where you can do unicast and unicast connections in a kind of the socket-like fashion, but still taking advantage of all the RDMA capabilities. And we are only attaching us to that layer of the stack because that is the layer that also our middleware is using. And if we can do the bridging at that layer, that's sufficient for us to migrate our applications. And so there's a particular focus, of course, with IB to ROCE on multicast bridging, because that is the majority of our traffic. And whereas unicast bridging is supported, but it is not as high performant as a multicast bridge. The bridge also can exist in multiple instances in the fabric and will then coordinate with the various instances, will coordinate with one another and provide redundant connectivity. So if one loses membership in a certain multicast group, for example, the other one can take over, or if the unicast traffic is routed across a certain gateway and it fails, then the other one can take over. So this also contains some advanced diagnostics for unicast and multicast connections, because we need to see what's going on there, and also the bridge needs to be able to make dynamic decisions on failover scenarios and take over the connection as necessary. There's also manual control over the failover. If we find that a certain host is misbehaving, we can, for example, shut things over and force a failover and force certain nodes to just stop. One of the problems also is we need to have control over multicast messaging rates. We found out that if we forward multicast traffic, we often encounter situations where we overrun the bandwidth of a certain link temporarily. That is a particular problem that we have to address. So the architecture of the IB to ROCE bridge is just 3 queue pairs that are open on both fabrics. And the single multicast QP is used to receive and send multicast traffic on multiple multicast groups. And that's where we also do the traffic control to make sure that we don't send too large bursts in one go. And then we have a unicast QP where we multiplex unicast traffic over a single QP so that we can forward RDMACM unicast connections. And then we have a control QP that is used to kind of control and kind of a partially replacement of the connection manager in the RDMACM layer, where we can take over a unicast connection and then forward unicast connections the way we want across this bridge. So a particular issue is, and a focus of this product is on multicast traffic, because that is the core component of the gateway. So how can you do this? So the trivial approach is simply subscribe to multicast groups on both sides and copy the content back and forth. Actually that works very well. If we do that, then the payload comes into user space, and the hardware already strips the headers and the particularities of the fabric of the packet, and we just send the payload to the other fabric, and the RDMA stack will in hardware put the other header on it. So most of the bridging is being done by the stack for us. And we don't really need to touch the payload at all if we don't want to. And we found out with that kind of approach, we have the ability that a single thread using RDMA cores can bridge 100 gig multicast traffic without a problem. We had some problems with it, but it can bridge 100 gig multicast traffic with some reserves actually. And that was kind of surprising. So that speaks for the efficiency of the RDMA layer. We had to avoid certain things like doing too much with the packets and doing some configuration on the system level to enable a thread to be fully dedicated to this task. But this was possible. And actually, we can then go to about 1.4 million packets per second on a single thread, even on a machine from user space. We're using a special technology that's included in Red Hat called no-hits full. That means that the kernel will not disturb the processing on a single core if you specify that option, and that the single thread can always be running on that core and will not be disturbed. That's a thread will then only be doing RDMA poll requests and RDMA sends continuously in a busy loop, and then you can actually get to this performance. We found out that if you don't do that, then the gateway can be overrun in a pretty fast way, because if you just miss one millisecond, you have already the potential of having lost over 10 million bytes of data. And it's very difficult to keep up or to catch up if you have lost that amount of data. And then one of the problems I mentioned earlier is that hosts can be overrun because the bridge can send actually too fast for the receivers. The middleware can only handle about 200K to 400K packets per second, depending on the application loads. So we installed a way to throttle the outbound packets. The bridge can actually serve multiple channels at the same time, but it must make sure that a single data stream is not higher than 100 to 400K packets. One option is there to use the hardware throttler as part of the global roles in the RDMA subsystem. So that allows you to specify the rates in terms of gigabits per second. And this is probably satisfactory in many instances, and does not require the use of any software. However, if you want to go slower than that, then you must use software. And so we also added a software implementation of a rate limiter. It allows a burst of n packets and then enforces traffic rates so that the endpoints do not get overrun. And if they get overrun, then we can configure the rates dynamically at runtime to control this. One of the particular issues here is that multicast on InfiniBand is different from multicast on ROCE. Multicast on InfiniBand allows back pressure. This means it can slow down the sender so that the receivers do not get overrun. That is not implemented on the ROCE. And I need to always make sure that we do not overrun the sender by sending too much, because the receiver has no way of telling the sender that it adheres too fast. So we can only use a fraction of the bandwidth. We cannot use the full bandwidth for multicast like we were able to do on the InfiniBand. Then we come to unicast traffic. Well, there's also a trivial approach. We asked our middleware vendor to modify their application so that they use the socket API for unicast instead of the RDMA API. So this works actually quite well. We can just use the kernel to route the unicast traffic. The kernel will strip the InfiniBand header, IPYB header, and all the other stuff, and add the IP headers properly, and everything will be fine. However, that then reduces the rate of communication that's possible with unicast traffic. We can't do 1 million packets per second. We can probably do about 100 packets per second if things are aligned well. And the latency of the traffic increases significantly. So this is potentially satisfactory if we don't run into any problems and you don't have any large amounts of unicast traffic. However, it may be necessary for some situations that we can actually process these things also natively as RDMA unicast traffic. So for that, we also implemented a way that the gateway can do math processing of the CIDR requests. The CIDR requests are those that are used by the connection manager of the RDMA subsystem to convert the port numbers to QP numbers. And those CIDR request and answer establishes these numbers between the sender and the receiver. And we are inserting the switch in between the receiver and sender. And the bridge then will give each side a port number that's satisfactory for the different fabric, and then connect these things and do the same forwarding that is used for multicast, also for unicast packets. This is a little bit more complex because we need to redirect the traffic away from the typical math socket of QP1, number 1. So we patch the kernel to be able to redirect the requests if there is a CIDR request to outside of the IP addresses of the local fabric. And so then the gateway can start its manipulations and take over the connection and do the forwarding of the traffic. Unicast performance is very similar to the multicast case, so we can do about 1 million packets per second, but the unicast payloads are usually much smaller. So we don't think it's possible to separate the links with unicast traffic like we could do with multicast. But this should also make it fully transparent for the application that will think that there's an RDMA connection going on between a node on the IP fabric and a node on the ROCE fabric. The software exists on GitHub right now. There's 2 components to this. One of them is basically an extension to the RDMA core package, where there is a new directory called IP2ROCE with all the code that's necessary to perform this bridging back and forth between InfiniBand and ROCE. This is still a work in progress, but we need to finish some things like documentation, and the handling of the QP redirection could use some work. Kernel patches are in a very rough form. They do work, but the handling is not that smooth as we wanted to. And we have several components of code in the source that we don't need anymore, maybe removed. Before we did the CIDR interception, we were able to do the same thing with a raw socket by just intercepting all packets that go through the gateway and basically finding these CIDR requests and then doing the CIDR requests based on the raw packet capture. But this means we have to duplicate all the traffic, and we don't want to do that in the final release. That was what I wanted to say, and I have 3 minutes left. Okay, great. Thank you for listening to me.
Thank you, Christoph. Are there any questions? Please enter your questions in the chat or raise your hand to be unmuted so we can hear you speak. Okay. I don't have any questions queued up, Christoph, so thank you very much.
All right, thanks.